Hello, my name is Berend Smit, and in this video we continue our discussion of free energy calculations in molecular simulations. What we had seen in the previous lecture is how we define free energy and why chemical potentials are important in classical thermodynamics. What we do here is to look at chemical potentials and free energy from a computational point of view. In fact, we're going to show why in a simulation a free energy calculation is much more difficult than, say, calculating the average energy. So, what is important in the free energy? Because from statistical thermodynamics, we know that the link between the free energy and statistical thermodynamics is done in the partition function. So here we have the partition function Q, and what is the partition function again? That is an integral over all the positions of the n particles. So this is an integral over the volume. So it's constant number of particles, constant volume, and constant temperature. So here we integrate over all possible positions of the n particles. So we integrate over all possible configurations. And what we do is we integrate the Boltzmann factor. Beta is 1 over kBt, and this is the energy of the configuration. Then in front there are two terms. One is the fact that the particles are indistinguishable. So if we relabel the particles, the particles don't have a label. So if you have particle 1 and particle 2 and you switch them, you switch the positions, you don't have anything new. That is so that this factor takes into account overcounting. This is the Broglie wavelength, and the Broglie wavelength is written here. And the reason we have this Broglie wavelength is for two, it's the integration over the momenta. So normally, if we do statistical thermodynamics, the partition function also involves integration over the momenta, but that is something you can do analytically. So the thermodynamics is determined by the configurational part, so the positions. So if we do this integration, there's typically a constant, and in the Broglie wavelength, this constant is such that we get the equivalent energy from a particle in a box, from a quantum free particle in a box. That's a quantum calculation, and if you do that quantum calculation, if you take this as this value for lambda, you get the same result. And what is important for the free energy calculations is to realize that this value, since it's an integration over the momenta, where there's also a Boltzmann factor in there, that it's dependent on the temperature. So it's a constant, but it's a constant that depends on the temperature. And here what I said, the link we make through the classical free energy to the free energy of our system is that we need to take the logarithm of this partition function. And this is here the equation for the free energy. So let's look at it again, and just to in many cases it's sort of important to have as a reference, and often the reference state we use in a free energy calculation is the ideal gas. So what is the ideal gas here is that there are no interactions, so the interactions are everywhere 0. If we then take the exponential of 0, we get 1. So this integral is then for one particle the volume, and for n particles the volume to the power n. So here we have the partition function of an ideal gas, and if we know the partition function of the ideal gas, we can calculate the free energy of the ideal gas, and from proper derivatives we can compute all kinds of properties of the ideal gas. So here you sort of see how we can define the free energy of an ideal gas, and that is just taking the logarithm of this function here. Okay. And here, if the number of particles is very large, we can replace the logarithm here with the Stirling approximation. So what is the Stirling approximation saying? That if we take the logarithm of n factorial, we get n log n minus n. And if n is very large, that minus n can be ignored, and then we get here, so we get v over n, and v over n is the density of 1 over the density, but then you have the minus sign that makes this one here, this minus sign, a plus. So this is an expression for the free energy as a function of the density, and since the free energy is extensive, it depends on the number of particles as well. Okay, So what is it we were doing in a Monte Carlo simulation? Recall, we didn't make a grid to try to compute this partition function numerically, and the reason was that many of the configurations, the Boltzmann factor, if we just take a random configuration, but basically we take a set of n particles and we give the particles a random position in our box, the probability that two particles will overlap is almost always there, that it's extremely close to 1. So every randomly selected configuration has a zero contribution to the partition function, and only in a tiny area we see that we have significant contributions. So what do we do in a Monte Carlo simulation? We sample only the area that is relevant, where we expect a relevant configuration, and here we sort of show that by the question is, how would you sample the average temperature or the average depth of the Nile? So you see most of these grid points, if you would do a numerical integration on the grid, have no relevance for the Nile because they're not in the relevant region of phase space, which is the Nile. So what you can do is you can step in the Nile and do some random, you make a step in the Nile, you measure the depth or the temperature of the Nile, and from that average you compute the average properties. However, free energies are related to the total volume of phase space, and that is accessible. So an equivalent of the free energy would be the total amount of water in the Nile, or the total area of the Nile. So those type of properties are nearly impossible to get from a sampling. You can ask people what their age is in a poll, but if you would like to know the total number of people in the city, you can get the average age of people in the city, but the total number of people in the city is something you cannot get from a poll. And that is the same in a Monte Carlo simulation. So if we look at that, what this difference is to say the average energy or the free energy from a sampling point of view, now let's look at the equations. So what is it we have for statistical thermodynamics if we calculate an ensemble average in a canonical ensemble? So what you do is, this is simple statistics, you integrate over all possible positions in our volume of the n particles, and you look as what is the probability of having that configuration in our ensemble, and with that weight you average, you compute the property A, say the energy of that configuration. So here we have the energy of this configuration, here we have the weight of this configuration, and what we do here is we integrate over all possible configurations. Well, this thing is normalized, so you can say this is proportional to the Boltzmann factor. So if we can write this easily like this. And here, so if you look at the statistical thermodynamics, this probability distribution is given, the normalized probability distribution is given by this equation, the Boltzmann factor divided by the Bernoulli wavelength, the indistinguishability, and the partition function. That's just following from the normalization. So what is it we do in a Monte Carlo simulation? In a Monte Carlo simulation, we generate a set of configurations. We select a particle at random, we displace it, and these configurations are distributed according to a probability distribution function. And that probability distribution function is given by our Monte Carlo process. So you hope that it would be the same or similar to the one you would like to generate, but for the moment we're just going to assume that we generate configurations according to the Monte Carlo scheme. So what is the average then? So this is an approximation of the average. So the average, if we would have an infinite number of samples, then it corresponds to integrating over all possible configurations and looking at the weight of those possible configurations in the probability that we have that configuration in our Monte Carlo sampling scheme. And what we're now going to assume is that this one, this distribution in our Monte Carlo scheme is proportional to this Boltzmann weight. just proportional. We do not know this constant. We don't have to know this constant, because if you know this constant, that's equivalent in knowing the partition function. So what is important is that we just say it's proportional, that we generate configurations proportional to the Boltzmann factor without having to know that constant. And if we substitute this expression in here, we see that the constant is disappearing and we get the same results. And that is the idea of important sampling, that if we sample our configurations with this Boltzmann weight, the average we get of our Monte Carlo simulation by just calculating the average energy of all the configurations we sample is an estimate of our desired ensemble average. But what you see immediately, that the thing, what is important of this equation, that we do not need to know the partition function in order to do that. And not knowing the partition function means we don't know, or we can't get our free energy from such a molecular simulation. So the advantage of important sampling is that we now have configurations that are important, because we generate only important configurations. The probability we generate a configuration with a very high energy is 0, but the price to pay is that we can't access the free energy anymore, and we need to do something extra, and that extra will be the theme of the next video.